suggested, it can associate to Lagrangian L inside X, deformation. I want to say the homology is the space of X. That should be some kind of completion of this deformation. And to, well, possibly and to L prime module. And then, moreover, I said, well, if you can actually make things a little bit better, so for each sufficiently strong norm on H1 and L, where here I remember that H1 is basically the realization of the fundamental group, so it's related to H0 of this. Can we can find a completion. So let's say with associated unit all, let's call it P inside coefficients. We can find completion H P of the space, which is basically intermediate between the usual homology of the base loop space and this completed homology, so that the Floer homology, this kind of module, is in fact defined in this. So if you can work over this ring here, that's basically the exact situation. You take exactly values which don't exist for a good reason. But this, and a priori, this is all you expect from graph compactness, but you can do a little bit better. So let me just now make some remarks, which I didn't have time to make last time, about the special case L, which is, so I'm going to use the topology terminology, which is aspherical. What that means is that the homotopy groups of L vanish for I greater than I. Well then, this homology of the basic space is supported in a single degree. And that has some wonderful advantages. That's the Floer theoretic deformation. Is unobstructed if and only if the count are holomorphic disks let me just say rigid holomorphic disks passing through a point vanishes. So usually in Lagrangian Floer cohomology, if you're trying to prove whether some Lagrangian Floer cohomology is well defined, whether some Lagrangian is unobstructed, then there's some kind of inductive procedure you have to do. You have to first check whether the disks have minimal area, and say some dimension, whether they can be filled by some bounding cycle, and then take that bounding cycle and use it with respect to the other infinity, to the other homomorphic disks to see whether their disks of higher energy can be cancelled and so on and so forth. And that involves things of different dimensions. But in this story, if you're in this special situation, and I just want to keep in mind that L equals a torus as an example, then there's really only one thing, really just this count. This just, if you're familiar with sort of like terminology, count against passing through a point means that the Maslach index is 2. Not only that, because the odd dimensional homology vanishes, okay, you get two consequences. The first consequence is the differential is necessarily trivial. And the second consequence is that there is no ambiguity in the construction of this object as some kind of object of the personified category. So usually there's some kind of space of bounding cochains. There's just no space of bounding cochains. Space of bounding cochains is also tricky. Bounding cochains is a point. Bounding cochains is likely the wrong term. Space of solution to the Markov equation. But anyway, the space of choices that you could put this object to is good. So this point is the corresponding thing, the corresponding Floer theory is uniquely determined. Now,
sorry, why does H odd vanish? What's the example?
That the homology of the base group space of some manifold, which is spherical, well, there's nothing. There's only things in degree 0. Nothing to. So okay, so if you see this, you ask yourself, this is somehow too trivial. Where did the interesting structure of Floer theory go? So, as I explained about the homomorphic disks of Maslach index 2, I told you what they give you. They give you this abstraction. So the disks of index 0, Maslach index 0, define the deformation of the product. Again, just to make clear, those of index -2 deform, well, they actually introduce, because this ring is necessarily formal for degree reasons, introduce a Massey product and 4, so on and so forth, up to index, I have to get my numbers right, so minus n minus 2, and then beyond plus 1, you get 0. Get no contribution. You get no contribution just because these moduli spaces are empty for index reasons.
So what you're doing now is you're spelling out what the deformation of this thing you get.
I'm spelling out what the consequences of this deformation existing. I haven't defined it, and I don't think I will define it, but I'm spelling out what the consequences are. Okay.
These are supposed to be algebraic consequences. But like this is just a translation of the words this deformation exists.
Yes, actually, it's a translation of the word this deformation exists, and it somehow comes from homomorphic curves. Because I say, then I want to know kind of what contributes to this. What, then I do some geometry. Okay. So let's specialize now even further and talk about the torus. And then this, I want to recall homology of the face with space of the torus is the same thing. Remember, we're working with Novikov over the Novikov field, so I'm going to just write my Novikov field as the round polynomials in n variables. In fact, you can write this invariantly when you do this business. It's better to write this invariantly as the group ring of H1 of L coefficients in C.
Question about the case of tori. You consider the case of some Sakomasu index 2 disk exist, like the case of toric manifold. Then this discount is not zero, but still you have a Floer theory. Okay. So
Let me just,
yeah.
I'm about to say that.
Okay, sorry.
It's okay. So this count of disks, okay, but when we complete, we get something like analytic functions, corresponding ring not of polynomials, but corresponding analytic functions. Sorry, we get Laurent series, which converge on unitary elements, i.e. when you specify that the valuation of these zi's, you just write zi, the valuation of bi equals 0 for all. And that has a name that gets written like this. Okay, so I said the curvature comes from some, there's an element here, let's write it n0. So we write n0 as a function. By the way, this says that you can associate to this Lagrangian torus some kind of potential function in space. This is supposed to be some instance of mirror symmetry. Now, in this complete generality, we shouldn't, I've written it like this, but this is not the algebra structure that this is equipped with. Okay? It's equipped with the algebra structure which has been defined. But I'll just allow myself a certain algebra structure. Possibly. And now, as Kenji said, it's well known that even if you have a Lagrangian, say Lagrangian, it's well known that if you look at Lagrangian torus fibers and the toric manifold, this function is non-zero, but there's still some interesting Floer theory to it. So what is this interesting Floer theory? Well, the answer is the matrix factorizations of this function. Okay? But let me express it again in this language which I'm trying to read. So to me it's the right language because then I can say it for any Lagrangian. So let me express it in this language. Well, this is going to be kind of some kind of cheat. So in the algebraic geometry language, I want to consider the ideal. So here you have to put some kind of closed ideal, some kind of topology generated by n0 and the Jacobian of m0. And the Jacobian of m0 is the thing generated by the expressions partial m0 over partial. And then I want to make one. And then I want to pass to the radical of this ideal and take the closure. Maybe it was the wrong thing to call this algebraic geometry. Let's call this commutative algebra. So this, okay, well, this commutative algebra picture has algebraic geometry or whatever, even though we're working analytically, so algebraic geometry interpretation, which is that we take the critical locus the function m0 as an analytic subvariety of, and again I'm going to be keep track of my H1 and coefficient in random. Okay, and this is some kind of form. You should think of this basically as some kind of analytic. It's a domain inside an analytic space. Okay. Now, if I have an ideal inside this ring of functions, then in particular, now maybe I'm going to say kind of, on this I'm going to put local systems. So we can associate to the ideal module, which is just ring of functions on I, okay? Which is of course a module over this ring of analytic functions, but it's also a module over the ring of Laurent polymers. As such,
What did you include in I?
so it's I. I took this thing.
Fine.
I took the radical because I don't want because here I want the subvariety, not the subscheme. And then I took the closure just so that I don't miss some stuff having to do with what's happening in it. But in this case, it should be anyway. Yeah, that's what I did.
There is any reason you need to take
Into what?
well, are there any mathematical reason you need to take radical?
I need to take the because of so that is a very, I'm going to make a conjecture, and I think that conjecture is true even if I don't put in the radical, but I couldn't find it in the literature that specifically analogous things to matrix factorizations. So let me make this conjecture. I think it's I want to make a conjecture. So let me just make that conjecture, and then I'll make a comment with y to the right. Okay. Associated to this module. Since it's a module over this, I said this is local system. A module over this, now let's go back again. This is just the homology of the base group space of L, and therefore, this gives rise to a local system. On our torus. Okay? So let me give a name to this local system. Let's give ECL. And now, I want to, so the following comment is going to be, this local system corresponds to this subvariety, okay? Your function and its derivatives vanish on that subvariety, which if you go through some addition, like third box called like homological algebra or like A infinity category, whatever you want to do to do the translation, you conclude that that is your Lagrangian torus L equipped with the local system EL is an unobstructed object of the chi category of our symplectic manifold. Now I want to make a conjecture, which is that the subcategory of the chi category. I guess I didn't have a name for my ambient symplectic manifold in X. Generated by your unobstructed local systems on our Lagrangian torus. So this category has many Lagrangians in it, so there's some kind of local system. Let's take the ones which are which have such that the underlying Lagrangian is L itself. embeds fully faithfully in a module in the category of modules over in the morphism, so which is spherical homology of L and L with itself. And this embedding is via just the unit amount.
Is this a conjecture about categories or about
It's a
infinity?
question about homological. It's a conjecture
Yeah,
about
this is-
homological algebra.
This is homological algebra.
Yeah, it's not. At this stage, I should have turned everything into just homological algebra, and that's the conjecture. And my point is that when this deformation, when in the Floer theory there is only this M0, and there is no higher order terms, and the ring structure hasn't been deformed, and the A infinity structure hasn't been deformed, this conjecture actually follows from something we know about categories of matrix factorization, which is that you write down you write down the subvariety corresponding to the critical locus, and that gives rise to a generator of, in this sense that mapping to modules is an embedding of the category of the corresponding category of matrix factorization.
So this is the same with the structure sheet of the critical locus.
Yes,
When you
generate.
map into matrix factorizations, generates. I
Yes.
see.
Oh.
And it doesn't generate. It can't like split generate, because if the critical locus is not smooth, then it's just not going to work. But it will generate in this. Should generate in this sense. I think that was proved by Simon. Anyway, and I believe the same is true with sub-scheme, but I haven't worked it.
I haven't understood what you meant by local system. Is it something much more horrible than just a flat vec bundle?
Infinite rec. This is a local system. The chains on the space of paths from a base point to an arbitrary point is what I call it local, is an allowable local system. So it's, you can call it a derived local system. Okay.
Is it known that this theory is zero dimensional?
No, it's not.
I mean, in that case, it is conditions.
In that case, conjecture is known
Okay.
because, essentially because it turns out that these higher order terms of the deformation, they cannot affect what's happening
Yeah.
to your, because it's just points. There's not much to do.
Wait, when L is zero dimensional, you said?
Yes. If L is zero dimensional, there's nothing. You can just prove this.
So in that case, the critical locus is actually isolated because it's just a
Yes.
point, and so like
And
you have like a lot more knowledge of matrix.
The point is that
factorization
even if you can,
isolated.
if you
It's
deform-
zero dimensional, but still can be non-reduced.
Yes, it can be
So there's something non-trivial.
There's something.
But
I didn't understand why is there any question when it's non-reduced? Because the Pusicelsky argument does it with every.
I guess I didn't manage to understand exactly. Okay, so I'm not doubting that it may be true. As I said, in the literature, I said I couldn't find it in the literature. I could extract this statement from something that Efimov wrote, and it may be that it resulted known using the sub-scheme as well. I just couldn't extract it.
think so.
It's probably true. But I wasn't going to claim it. So, but again, as somebody said, as Vivek said, it's now homological algebra.
Yeah.
So, okay. So I just wanted to say this because to me this is one advantage of this point of view where you take this big system and you try to put out the data in this local system, which is the change in the big blue space. It is supposed to remember everything. Unfortunately, this tells you that it may be, and you know from examples that it may be obstructed even though there are unobstructed objects. But this tells you what they should be. Okay. So now, having basically finished what I meant to say last time, let me continue with the goal for today's talk. So today I want to just say some words about how to go from something local to something global.
Can I ask, why is the base blue space enough? Why don't you need like all the homotopy theory of
The chains on the base loop space knows about all the homotopy theory. Yeah. All the homotopy groups.
Yeah, okay.
No, chain level.
Chain
You know
level.
that? The manifold is the classifying space of the base loop space. So it knows that. I'm sorry. So let's assume that we have x q, and so I'm going to basically not do what I'm supposed to do for this concept, which means I'm going to eliminate log crossing. Well, I'll have some kind of very simple I'll put some assumptions to make sure there's no log crossing. This is a Lagrangian force vibration. With no singularities. And I will write x sub q for the fiber over point q. Okay. And what's going to happen basically is that this x sub q is going to play the role of the Lagrangian L that we had until that point. L. And now I have let, okay, this is going to be very annoying. So let L be inside X be some other Lagrangian. Well, let's just say Lagrangian manifold. Okay. And the goal is to reconstruct the Floer homology of L and ultimately kind of the entire Floer theory of L from Floer theory of L in the fibers. And let me just put here that for now. But this is not really the right thing. You don't want to put in the fiber, you want to put instead that locus. And so, which kind of makes some sense. It's some kind of like spectral sequence for the projection from X to Q. So we'd like to recover this with itself. You project down and you integrate over Q the Floer homology. L. And this L plays the role of L prime. So L prime in the previous section. So this one is going to be fixed, and these are going to be varying in flux.
Is everyone here compact?
Everyone here. That's a good question. Right now, let's say yes. I mean, since I said this is a Lagrangian torus vibration, the only question really is about X and L. Right? And let's just say yes for now. I don't want to. I haven't written it in the non-compact case. Okay, and so what do we know? Well, we have these great. So let me just recall from Kenji's talk that Q is an integral affine manifold. And what I really mean by that is that if you take a point Q inside Q, then you can find the neighborhood which embeds naturally inside H1 of XQ with R coefficients. And this, of course, has an integral structure. That's the way people normally state it. Now what I want to do is I want to pick this U to basically, inside of U I can pick some P, which is some convex polygon. So I will just, you can think of P as living inside Q, or you can think of P as living in H1. And it's basically the same thing. this convex polygon gives rise to a norm. It's the unit ball for a norm on H1. And therefore, we know that it gives rise to a deformation. So this gives rise to, I'm sorry, there's no deformation because anyway, it gives rise to a completion. Maybe it's sitting up there. H, P, star omega L, omega. Okay. And what I'm going to do is I'm going to write this, define this to be gamma. Okay. So I want to talk about how to think about gamma. So P from some kind of mirror point of view. So the mirror will be a space, say A, an analytic space. Y. It will also project to Q. Okay? And so therefore we can ask ourselves, what is the part of this analytic space which lives over P? Let's write Y sub P, this that lives inside P. And that, to describe that, I just use the other picture. P lives inside H1, L with coefficients in R. Last time I explained that there is this valuation map from H1 of L with coefficients in lambda star. And this lives inside here, and it's just the inverse image.
L or X?
Thank you. And it's just the inverse image. Now, I said this is supposed to be an analytic space. All I will say right now is this is, you can identify it as lambda star to the n. So if you don't want to think about analytic geometry over this ring, you can just pretend this is like C star to the n, and I take a map to Rn, which is log of the absolute value of Z. Then I take a domain inside Rn, and a convex domain inside Rn, and take the inverse image, so you get some kind of complex analytic domain. It looks a little bit like a product of n. So in dimension 1, you get complex. Okay. So so I said this is an analytic space, so I better be able to talk about its ring of functions. The ring of functions up here analytic functions on which converge on YP. Okay? And if you go through, what I said last time, this is exactly gamma sum. So last time I claimed that we can associate to L called L prime, a module over over this thing which is now called gamma p. And then I said, and we'll come back to this in a second, which is invariant. We'll come back to this. This is something slightly done.
Is something you said last time supposed to tell me enough to check the gluing statement that's...
There is actually, this is partly why I said there's no wash crossing. There is basically, the gluing is tautologous.
We don't have to check like all polygons and all somehow.
The gluing is tautologous. So, you know, this, so, this thing is defined as an analytic thing inside lambda star to the n. Okay? Let's say you pick another polygon p prime and they intersect. Then they embed in the same lambda star to the n because they both embed inside the cohomology of this phi. Pick it at the end. So there is no. So maybe then you could say, oh, you know, if I think of this p is living in the cohomology of this one versus living in the first cohomology of this one versus first cohomology of this one, how do I know that's the same analytic structure? Okay, maybe you want to check that, but that gives you some kind of vector from here to here. You just add that vector, some kind of simplest possible analytic transformation you can make. Now, add means multiply because you're working. Okay, so let me just leave it like that. So invariant under choices. So in this language, this means some kind of coherent sheaf. But I didn't say what kind of module, but maybe you'll grant me coherent sheaf over YP. Okay. So if we could glue them together, then we would get a coherent sheaf on Y.
I think more precisely you have a complex of module.
I'll be precise.
Yeah.
Just,
Yeah.
I'll be precise in this.
Yeah.
So that's the idea. But now, if you want to glue together coherent sheaf, the thing is that this coherent sheaf, it's not just, it really is a kind of graded coherent sheaf. You took the cohomologies and put cohomology. So you want to glue it together, and now you have some ambiguities in how you glue them together, which means if you don't want to work past the cohomology, we should work at the chain level to do this glue. At the chain level, to get it. So I want to explain what that means. And in the process, I will manage to explain why this is coherent.
I have a question about why it's coherent. Like, you know, so some aspects of this are similar to like Abouzaid construction. Why does that give me a constructible sheaf? And this one gives me coherent?
The two-word answer is because that's already two words. Sorry. They vary Lagrange. They use exact isotopies of Lagrangians, and these are not exact. That's basically.
Just to check, you also want that the Q is simply connected for you to not have any sort of possible monogamy to do this?
No, that's not a problem. No, that's not a problem. The only ambiguities come from if you have polynomial. If you have no, this is not a problem. I mean, there may be some monogamies, but those are just encoded in the gluing of this Y itself. That's fine.
For instance, if I think I have I think I have something that has a singular fiber there.
Yes,
But I
remove
just-
the singular fiber. Remove the singular fiber. There's no disk left.
No, that there is other fiber that could have some. Oh yeah, there is no display. Okay.
So, are you saying that somehow this construction would not work or would give something trivial if I took exact deformations?
It'll give you a local system.
Would it first give me a coherent sheaf, which I then also learn the connection on, or would it not give me?
That's an interesting question. No, I don't think that's what it would give you. I think, you wouldn't see the kind of, not as I see it right now. The analytic direction comes from the fact that H1 is non-zero, H upper 1 is non-zero, and we are moving non-trivially in that H upper 1. And if you have an exact deformation, by definition, you are not moving that H upper 1, so you're not getting this analytic direction. Okay.
Well, you are getting it. It's just trivial. Exactly what he said.
Yeah, but no.
No, it's locally constant, and then you analytify.
It's really locally constant over a point.
But you're not moving it.
Or you can't move in the p direction.
Yeah, I think I would like to say that in that case, this base, if the family is an exact deformation, the base is not an analytic space. There is no analytic structure on the base.
There's no affine structure or
There's-
anything, yeah.
There's no affine.
And I suspect there'll be some examples where things are much more complicated and we may be able to see something like this, but it's not that case. Okay, so we need to make this precise. But the module over YP arises from what I called last time CF star of omega hat P. Now it's called this XQ, comma L, okay, which was defined. Now things be a little bit more precise. If L is transverse to XQ.
Well, you can ask my question one more time. Suppose I start out with a Lagrangian, which is like exact, not exact, like it's not deform it to the exact situation.
You mean suppose you can do this?
Suppose I had a family that began as
Yeah.
would I then get a local system, like a coherent sheet, which I then learn the connection on?
No, that's not any different from the case that Mohammed's talking about.
So, okay, maybe we can talk later.
Okay,
but
okay.
Here's what you want to imagine. Take the space of all Lagrangian deformations. Okay, Hamiltonian and non-Hamiltonian. Inside that space of Lagrangian deformations, you have these leaves, which are the Hamiltonian leaves. Okay, so you have some kind of sheaf on this space, which is locally constant in the Hamiltonian direction and analytic in the transverse direction. So you make that precise, and that'll be. So this is a sum over all intersection points of this chains on the space of paths, also completed in XQ, so I'll write that, between our base point, which I have a name, and X. Okay? So the point is, this thing is basically a rank 1 module. I mean, it's basically free of rank 1. We know, except the terminology may not be right, but let me say it like that. Of rank 1 over, not quite gamma p, but over the thing with homology gamma p. So let me just write that. And then you write homology is free. It's free of rank 1 over there. So that means that this thing is a finite, so this gives rise to a finite complex of gamma p modules.
Of three gamma modules.
Sorry?
A finite complex
Three
of
gamma.
threes, yeah.
Hence, the cohomology is a coherent sheaf. And so, of course, once you're here, you say, well, this is not the right notion, this is the right notion, so we will call this being perfect. And we will take our perfect modules over the real functions of the local pieces and we try to glue them together. Now, at this stage we have a small problem, but actually this small problem is just an example. I mean, so you know how to solve this small problem, and everything, the local to global issue kind of disappears. So let me say it again. So, in order for this construction to make sense, for this module to be defined, for this complex, let me just be clear, to be defined, we need the transversality condition. Otherwise, I can't write it down. But it's implausible that this condition holds for all q. There's no reason for your Lagrangian, which you know nothing about, to be transverse to all the products. So, in my statement that there is some module over this ring which is associated canonically to L. If I want to write down an actual chain complex, I can't quite do that. There's no chain complex that's canonically associated to L. And in fact, what I have to do in order to achieve that is shrink E quite a bit. I'll say a few words about that. And then go from something which is obtained on very much smaller local pieces and then glue them together. But of course, that's the local problem, but then that's also the global problem. So if you know how to do this, then you know how to do the whole thing. I don't remember when I started.
You have 13 minutes.
Thank you. Okay. So what needs to happen? So what you need. So in addition to transversality, we need something which, so either of the following conditions. So let me just say, we need that P is small enough that the isoparametric inequality, so parametric inequality implies convergence. So the isoparametric inequality is something I wrote down last time. It says that we can bound the area, it says basically the area of a disk is greater than some constant times the length of the boundary of the disk. Okay? And this constant is some constant, and whatever this constant is will tell you how big P is. Well, this constant depends on the geometry of L. This depends on x cubed and okay, to make it clear that which one is L, which one is L prime, and both of them are needed. Okay? And Kenji has this wonderful trick, where you don't actually have to worry about this analytic part of doing this estimate, but it's just a replacement. It's basically it allows you to do something geometric instead of something analytic. So Kaya, you can replace this estimate by the existence of a diffeomorphism And I'm stressing diffeomorphism because I don't, so let's call it psi q prime, so all q prime in P. Okay, you need the diffeomorphism to do the following, such that one, it preserves L pointwise. Two, it maps the fiber of Q to the fiber of Q prime
What is this a map from and to, this 5QQ prime?
from X to itself.
And you emphasize diffeomorphism as opposed to symplectic or
Yes,
as opposed
yes.
to homeomorphism?
So, pletomorph. And lastly, it preserves the tameness of almost complex structures. So what does this do? So let me draw the picture here. So let's say you took this fiber and say, so what you want to say is that the holomorphic disks with boundary on the green one and the holomorphic disks with boundary on the yellow one are the same, except for the fact that the areas have changed. Okay? And this psi allows you to do it. So the key thing is that psi q prime turns disks with boundary on xq into disks with boundary on xq prime. Well, they're the same, so what has changed? Well, this only thing that changed is the area, and that area is how you, and that area is what's recorded by these parameters when we're working over the basic space.
So does number 3 mean that there exists some almost complex structure which is taken with respect to symplectic form and its pullback?
Yes. But you, in practice, I mean, once you do this, you may want a little bit more. You may actually want this path to be like isotopic to the identity, and you probably want the tameness to be preserved by the entire isotopic. I mean, and later things build on this, and we'll have family. We won't have anything because I'm stopping in 5 minutes. But in the full story, you have kind of families of these things parameterized by complicated geometric objects to encode the higher coherences in the gluing of chain coordinates. Anyway, so the outcome of this.
So, as you're erasing, what about that thing that you just erased? It doesn't show up. That's what's hard. It doesn't show up because you erased it.
No, it's not about this. That was, I finished that and I said, now let me talk about how to go from local to global. So that thing is going to show up when you have homomorphic disks with boundaries on the fiber and you try to and it tells you what you should use. So let's talk about that later. Sorry, okay. So in the real story, so closer to the truth, you should pick for each Q in the base, and later we will just make this be a finite subset using compactness of the base. A Lagrangian, let me call it L sub Q, which is Hamiltonian isotopic. To L. Okay. Then with respect to this choice, so then we can define, we get, call it M sub Q, which is a complex of, again, free finite, but I'm not going to write that, modules over gamma P, where P is a sufficiently small neighborhood of Q. Inside inside the base. And now, the claim is like this. If you had chosen these, so you fix the choice of Lagrangians now. But if you had chosen these p's to be sufficiently small, I should have written, should have had a piece of q. If p's of q are sufficiently small, then whenever you encounter the following situation, so this is piece of q, this is q here, piece of q prime, okay, and there's some point q double prime in here, okay, then you can find p q double prime, okay, such that there exists quasi-isomorphism of gamma p q double prime module, modules or complexes between I'll call it MQ tensor over the ring of functions on this thing called gamma PQ with gamma prime and MQ prime tensor over the other one. Okay? So if you think about trying to glue together some kind of complexes of modules over some affine pieces of space to build something global, this is the data that you need. Okay? But you don't just need this data, because we're working at the chain level. Well, actually, even if you're working at the homology, you don't just need this data. You need this data, and you need to know that it's compatible when you look at triangles. And it is not, in general, but the abstraction can be easily understood. The abstraction to make this into a sheaf at the level of cohomology is exactly the abstraction to having a Lagrangian section. So this gives rise to a twisted coherent sheaf by passing to homology. After taking homology. But if you want to build something at the chain level, then you need not just this map, but also a quasi-isomorphism whenever you take a triple intersection and you restrict from here to well, from here to here via here, whatever. Anyway, you can imagine. You have some okay, and then some further thing when you have 4 things and 5 things and blah, 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 which seems like it might be completely insane because I said that these things have to be sufficiently small. But you're lucky because the covering dimension of the base is n. So you only have to go n steps down. You only have to shrink things n times, and once you've shrunk things n times, everything's okay, and that's all the data that you need to glue. And that's all I have to say. Thank you.
Questions?
So I think in the case base is nothing to connect with, it's not all right. If you have a loop, then kind of this structure on the fiber may have a twist here. So probably you need some more.
So in this, I should have said, the obstruction to this being defined is the obstruction is having not a Lagrangian section, but a spin Lagrangian section. A Lagrangian section which is spin.
Yeah, but also kind of family of Lagrangian submanifold should have some kind of compatible family of spin structure.
Yes, but
That's the same thing? Or?
it is controlled by the base.
And for example, in the case of this monodromy, you have this 1101, which does not preserve spin structure. So if you want to kind of construct this family of homology pairs this time,
Yes.
if you go around, you have some twist in it.
So changing the spin structures corresponds to just changing the local system.
Yeah. So
So it's just the action of the
yeah.
action of the local, but that action of the local system is recorded in here
Okay.
because that's the monodromy
Yeah.
on H1. So that doesn't.
Yeah, I understand.
So is there a more geometric way to describe the germ that's twisting the G?
Yeah, if I had time, but I meant I kind of hinted at it. But yeah. So So if you take x over q, then you can ask yourself, what is the obstruction to the existence of a Lagrangian section which is big? And you can write this as an element. This obstruction lives in H2 of Q. Okay, now I have to say some words. I have to say Q is an integral affine manifold. It has a notion of affine functions in the sheaf of affine functions. Okay. And this thing maps to H2 of Y with coefficients in O star. And so that's the truth.
Did you explain why? You know, in the end, you wanted to say that now I have the sheaf, I take Hom from the sheaf itself or whatever, and that's Hom now. Did you explain why this is true?
Why? No, I didn't. I didn't even explain that there was a map. But there is. so I constructed this sheaf,
Yeah.
and basically these sheaves are like Floer homology of my Lagrangian with fiber. Okay, so then we need to prove that all these constructions of gluing are compatible with the natural data map. Yes, that's exactly the right idea. It's that painful. And then once you glue them together, so that gives you a map. And then you need to prove that map has some properties.
Yeah.
So you can prove that map is in Jack. I don't have to prove it yet. So it's faithfully embedded, not fully faithful.
Or would you say that you use about the fundamental classes you got to prove that one?
Yeah, I think I can prove more, but somehow less.
You don't frame
Not
it.
today. Okay. Tony?
Okay, thank you.